Alright, so now moving on, I said that I'd introduce you to the concept of the big M method and why we need to use artificial variables, why we need to use excess variables. So consider the following linear programming problem. We are asked to maximize z, which is equal to 3x1 plus 5x2, subject to x1 being less than or equal to 4, 2x2 being less than or equal to 12, and 3x1 plus x2 being equal to 18. Well, to transform these constraints into a form that we can use in the simplex method, these two are simple. As they are less than or equal to constraints, your mind must immediately tell you that we should use slack variables. And we add slack variables. And in this scenario we have an equality. So we must introduce an artificial variable. So we add an artificial variable. So what this becomes is x1 plus slack variable 1 must be equal to 4. 2x2 plus slack variable 2 will be set equal to 12, and 3x1 plus x2 plus artificial variable 1, because this is the first artificial variable that we're introducing, must now be equal to 18. And then you might ask, well, what's the point of this artificial variable? Why am I adding it here? Well, the problem with this equality constraint is that we have a bit of uncertainty as to what will happen to the maximization function of z. And what the big M method is trying to do is it tries to help us to get an initial solution to start off our simplex method with. So what happens and why it is called the big M method is because when we are trying to maximize z, we introduce some variable m that is very large, arbitrarily large, so that when we're trying to maximize a function, we penalize the maximization by subtracting m times that artificial variable. So if I try to make this z as large as possible, and this a1 bar is not 0, if it does not equal to 0, then this maximization function will immediately drop to a very, very large negative number, because we choose m to be so big that z would be a very negative number if a1 bar does not equal to 0. And this is the reason that it is done. We introduce artificial variables to be able to have enough columns to start the simplex method, to have an initial solution, an initial basic solution. And with this initial basic solution, we would simply set S1, S2, and A1 bar equal to the right hand sides respectively, so 4, 12, and 18. And I'll show you now how we would start off this simplex tableau. So firstly, I told you that we introduced a penalty on maximizing z. So we are now going to maximize z minus 3x1 minus 5x2 plus ma1 bar, subject to x1 plus s1 must be equal to 4, 2x2 plus s2 must be equal to 12, and 3x1 plus x2 plus a1 bar must be equal to 18. So firstly, writing your simplex tableau, you would notice that the columns for x1, x2, slack variable 1, slack variable 2, A1 bar, and the right hand side will be -3, -5, 0, 0, and A1 bar will peculiarly be M, but our right hand side will be 0. And what's the rule for a variable being basic? If a variable is basic, all entries in its column must be 0. So I'll fill in the constraints now. So x1, 1, 0, 1. What do I notice here? M is not 0, even though artificial variable 1 is one of the basic variables. Here is our column for our basic variables. So S1, S2, and A1 are our artificial variables. So we have to, before we can start the simplex method, we have to go and say row 0, which is our very first row, minus m times row 1, 2, 3 to become the new row 0. Because we need to eliminate this m in the first row. So what we're going to see is we're going to have -3 minus 3m. Then we're going to have -5 minus m, 0, 0, 0, and -18m. So this is how we first find the first row 0 that will allow us to start the simplex method off with. Okay? Alright. So this is our initial tableau. Or table if you wished, of the simplex method. And we notice that our basic variables are slack variable 1, slack variable 2, slack variable 3. And this is our transformed row 0 equation. Now, again, if we're doing the simplex method, our first job is to find the entering variable. And in this scenario, we can clearly see that if m is a very large number, then we know for a fact that -3m is going to be much greater than what -m is, in terms of absolute values, of course. So, it's clear to us that x1 is our entering variable. Now we need to do the minimum ratio test. So you look at the right hand side, 4 over 1 is 4, 12 over 0 is inconclusive for the minimum ratio test, and 18 over 3 is 6. So it's clear to us that this is the smallest row. So that means that slack variable 1 must leave the basis, and x1 will enter. So entering variable x1, leaving variable is slack variable 1. So let's write our new row. It's 1, 0, 1, 0, 0, 4, and then we need to transform row 0. So we're going to say row 0 plus 3 plus 3m, row 1, to become row 0 new. Because we need to eliminate this -3 minus 3m. So -3 minus 3m plus 3m becomes 0. -5, this one remains unchanged. This becomes 3 plus 3m, 0, 0. And then we have -18m plus 12 plus 12m. So this becomes 12 minus 6m. And then our subsequent rows, as this is a 0, we simply copy this row again. And we say for row 3 minus 3 times row 1 to become row 3 new, So 3 minus 3 is 0, 1, negative 3, 0, 1, and 18 minus 3 times 4, 18 minus 12 is 6. So this is our first iteration, and what we can see here is that our solution is not yet optimal because we still have a negative entry in row 0, negative 5 minus m. Our basic variables are now x1, slack variable 2, and artificial variable 1. So again, we do the simplex method. Our entering variable is x2 from this column, we can see, and then we need to do the minimum ratio test for the right hand side. So the ratio 4 over 0 inconclusive, 6, and 6 over 1 is 6. So as you notice, these two ratios on the right hand sides are both the same. What this means is that if I now select some variable to leave the basis, say I select artificial variable 1 to leave the basis, then row 3 would simply be this. And now to change this entry of 2, to make it 0 here, I have to say row 2 minus 2 times row 3 to become row 2 new. And what happens here is that if you notice 12, our right hand side, 12 minus 12 is 0. So we encounter a problem here. A basic variable, namely S2, is set equal to 0, but it must be basic. This is a very, very, very important concept, and something that will catch you out likely, is that this is called a degenerate solution. Why? Because a basic variable is forced to have a 0 value. And because of this, we can't carry on with the simplex method, so we can't carry on, and we state that a degenerate solution exists. Or that the degenerate solution is causing us to not be able to carry on. So, how do you spot a degenerate solution? How to spot a degenerate solution? We look for a basic variable that is equal to 0. That's how we spot a degenerate solution. And the moment if you see that it's equal to 0, stop. Don't try to carry on with the simplex method because your solution is degenerate. It will not yield an answer. Because we won't be able to have a variable that will be leaving in the next iteration. So that means that our solution is degenerate. No solution exists. Okay? And I'll change this problem here to a form that will enable us to carry on and solve the big M method, so that you can see that it does actually work and that it does yield the result. Okay, so as was seen, the previous solution was a degenerate solution because we had a basic variable that was set equal to 0 by the operations that were carried out. So I have altered our original equation to become this new equation, and notice that the changed variable is only the x2. It has now become 2x2. So this means our first iteration will also be changed. Its 0th entry in the x2 column will be -5, -2m, and the element in the row 3 as well will be changed to 2. This means that the ratio test will now allow for a unique leaving leaving variable, meaning that A1 bar will leave the basis, leading to the subsequent table, where again we check for optimality. We notice that this is not, the conditions for optimality are not met, as the S1's entry in the 0th row is -9/2, which is not positive. Hence we must have S1 entering the basis, and we carry out the minimum ratio test. We find that S2 must be the variable that leaves the basis, because it has the lowest value in the minimum ratio test. Then we go on to a third iteration of the big M method. We notice now all the entries in the 0th row are positive. All the solutions on the right hand side are also positive, so we have no degenerate solution, as there is no 0 or no negative value. And then finally we can conclude solution is optimal. And with this value of z being 32, and our optimal solution in terms of x1 and x2 is equal to 2 and 6. And that's that. That's how we carry out the big M method. So firstly what we do is, if we are maximizing the problem, we add a penalty when we have shifted the equation to the left, or simply I can write it down as this. If we have a maximization problem and we have artificial variables present, then if you have a maximization problem, you penalize it by subtracting m times the artificial variable. If you have a minimization problem, then you add m times the artificial variable. This is the very first thing that must go through your head once you have transformed your equation and you identify that there are artificial variables. So I examine it, I notice that it's a maximization problem. So if it's a maximization problem, we subtract the artificial variable, and then if I bring all of the variables to one side, to the left side, then the subtraction becomes an addition of MA1 bar. Then to start off our simplex method, we must remember that the column of any basic variable has to have 0 entries except for where the 1 stands. So all these must be transformed to 0. So that's why we took row 0 and we transformed it to a new row here in the very, very first example. So we saw that our row 0 had an M instead of a 0 in the A1th column in the 0th row. So we had to subtract m times row 3. This gave us this. So thus we are able to start the simplex method. We have our very first iteration. And once you have that settled down, all you have to do is run the simplex method as usual, remembering to check for optimality, carrying out the minimum ratio test, and working through the problem as you go. And once you reach your final iteration, if all of your solutions are positive on the right hand side, for your all your basic variables are positive, you don't have any degenerate solution, and optimality is met, then we can finally conclude that we have an optimal solution. And in this case, its value is z is 32, and the optimal solution in terms of x1 and x2 are written as 2 and 6. So that's how we carry out the big M method. Those are the things you need to look out for, and also the definition of a degenerate solution is when a basic variable is forced to have a 0 value. So we cannot carry on with the simplex method.